I am Dr. W. Gurgale from Kamala Nehru Mahavidyalaya, Nagpur. Today we are going to discuss the stability constant of the complexes, and we know that there are two different types of stability of the complexes, and one is a thermodynamic stability and second is a kinetic stability. And thermodynamic stability is classified into stable and unstable complexes, and kinetic stability tell us about the whether the complex is labile or inert. And again now we are going to see in the next part, that is the what is meant by stability constant, and what is the stepwise stability constant, overall stability constant, what is the relation between stepwise and overall stability constant. All this part today we are going to discuss in today's presentation. So today's topic is thermodynamic and kinetic aspects of metal complexes, and here we are going to discuss what is the stability of the complex, what are the after that types of stability of the complexes. All this part we are going to discuss in today's presentation. And here the formation of complex in the solution, there are two kinds of stability complexes are considered. And the formation of metal complex in aqueous solution is a matter of great importance, and especially in inorganic chemistry. All the metal ions in the aqueous solution exist at M(H2O)N, that is some water molecules exist with the metal ion, and in this case the interaction between hydrated metal ion and the ligand in forming the coordination complex is regarded as a Lewis acid-base reaction. The stability of the complex formed is related to thermodynamics. The terms stable and unstable are thermodynamic terms representing the tendency of the species of coexist or not. Complexes can be classified into two general types, labile and inert. Labile complexes react rapidly, whereas inert complexes react slowly. And so this is about the stability of complex. And now we are going to see what is meant by thermodynamically stable and unstable complexes. So in this part, this thermodynamic stability is a measure of extent to which complex species will form and to be transformed into other species under certain conditions where the system has reached equilibrium. So in this case, this stability of the complex depends upon the strength of the linkage between the metal and the ligand. It can also be, we can say that the amount of association between the metal and ligand and that occurs in the solution at equilibrium. On the basis of thermodynamic stability of the complex in the solution, these are classified into stable and unstable complexes. And stable complexes are those which possess sufficient stability to retain their identity in the solution. Stable complexes are those which possess sufficient stability to retain their identity in the solution, while unstable complexes are those which are inversely dissociated in the solution into their component. Stable and unstable complexes have also been called penetration or normal complexes. For example, when ammonia is added to the aqueous solution of copper sulfate, there is a change in color because blue Cu2 plus ion is converted into deep blue ion by the addition of ammonia. So here the reaction is shown, how the complex is formed. So this is the reaction which is shown here. This is the blue color copper or copper sulfate. If you take, so copper ion is a blue, when ammonia is added we get a deep blue color complex, tetraamine copper 2 plus complex. And for this reaction, this is the equilibrium reaction. For this, equilibrium constant can be determined. Equilibrium constant K equals to concentration of product upon concentration of the two reactants. So here the value for this complex is 4.5 into 10 to the power 21. So it is greater. And so this is the and here we can say that high value of K means complex ion is thermodynamically stable, and therefore equilibrium constant K refer to the stability constant of the complex, and the higher value of K greater is the stability of the complex. On the other hand, we can say 1 by K is known as the instability constant. So K is the stability constant, and greater the value of K, stability constant, the complex is more stable. And second important stability is a kinetic stability. So two stabilities are there, thermodynamically and kinetic stability. So in case of kinetic stability, it refers to the speed or rate at which the formation or dissociation of the complex take place, leading to the attainment of equilibrium will take place. This kind of stability deals with the rate of reaction of complexes in solution, the mechanism of the chemical reactions such as isomerization, racemization of substitution, electron transfer reaction, formation of intermediate of the complex, activation energy for the process, etc. These are the process in which it is found, and the complexes have been classified on the basis of kinetic stability into labile and inert complexes. So on the basis of this kinetic stability, the complexes have been classified into labile and inert complexes. The complexes in which one or more ligand in coordination sphere can be rapidly replaced by other ligand, and these are known as labile complexes. The complexes in which one or more ligand either cannot be replaced or can be replaced with a difficult by other ligand are known as inert complexes. Under such condition, the coordination compound will be thermodynamically stable and kinetically unstable. So these are the second type, kinetic stability, and also there is a relation between thermodynamic and kinetic stability, which is shown here that as we know, to show the relation between thermodynamic and kinetic stability, the labile and inert complexes show the rate of reaction at which the substitution of one ligand by other ligand occur, and these are represented as a kinetic stability of the complex. It should not be confused that thermodynamic stability term, that is stable or unstable. Thermodynamically stable complexes may be labile or inert, and thermodynamically unstable complexes may also be labile or inert. And there is no correlation between thermodynamic and kinetic stability term. For example, here the table is shown, and three complexes are shown here, and these three complexes are tetracyanonickel 2-, and this is second and third. For this, thermodynamically these complexes are stable. One stable, this second is also stable, third is also stable. But kinetically, first complex is labile, second is moderately labile, and third is inert. So see, the thermodynamically they are stable, but the kinetically some complexes are labile, some are inert. So in this way, we can say that if the rate of exchange of radiocarbon labeled cyanide is measured, we find that despite the thermodynamic stability, one of these complexes exchange cyanide ligand very rapidly, that is labile, second is moderately labile, and third is considered as a inert. To decide whether the complex is labile or inert, a good rule is that complexes that react completely within about 1 minute at 25 degrees Celsius should be considered labile, while those take longer time should be considered as inert. So this is the one of the test. It may be concluded that inert complexes are not necessarily thermodynamically stable, and the labile complexes are not necessarily thermodynamically unstable. Thermodynamic stability of the complex depend on the enthalpy of reaction, while the kinetic stability of the complex depend upon the activation energy. So this is the relation between these two types of stability, thermodynamic and kinetic. And here now, what is the stability of the complex? We are going to discuss. That is, the stability is a term which is often used rather loosely or in open. We can say that there are two types of stability, thermodynamic and kinetic, that we have seen. And for the reaction, general reaction, if you consider metal plus forming n number of ligand forming the complex M-L-N. So N-L is the number of ligand, and for the general reaction, that is metal M plus ligand L, and to form the complex M-L-N. And L is the number of ligand, M is the metal, and in this case we can say that the stability of the complex can be expressed by the magnitude of equilibrium constant for the association reaction. Stability of the complex is generally characterized by the equilibrium constant of the reaction of their formation from the constituent, or by the dissociation of the dissociation constant of their dissociation reaction into the metal and ligand ions. the equilibrium constant is a measure of stability of the complex. So for the general reaction, m plus n equal to mln. So equilibrium constant is equals to concentration of the reactant product upon concentration of reactant. So we can say that the equilibrium constant K is a measure of stability of the complex. Greater the value of K, greater the stability. Smaller the value of K, smaller the stability of that complex. So based on that, now there are two types of stability constant, and one is a stepwise stability constant and second is overall stability constant. This is important part of this stability. So first is what is meant by stepwise stability constant now. So yes, in case of stepwise stability constant, the formation of complex species in the solution from its constituent, that is metal equilibrium in the solution, can be expressed in two ways and shown here. First, according to the J theorem, the formation of complex in the solution take place by the stepwise addition of ligand to the metal ion, and the formation of complex MLN may be supposed to take place by the reaction which are shown here in this slide. So here this is the stepwise stability constant, and one stepwise we are adding the ligand. So here metal M plus ligand L, and K1 is the stability constant and Ml is the complex form. For this K1 equals to, this is the K1, and so rate constant equals to K1 equals to concentration of metal product upon concentration of ligand. So this is the first expression. Again now take this Ml here and add another ligand here. So stepwise addition of ligand is taking place and we get Ml2, and K2 is equals to this one. In the similar way up to n times, up to n minus 1, mln minus 1 plus n, l, and forming m, l, n. So this is for this. So in this way K1, K2, K3 up to Kn we can write the expression. So equilibrium constant K1, K2, Kn, these are known as the stepwise stability constant for their complexes. So this is the one expression that how the stability constant can be is there. So it is the first is the stepwise, and in case of stepwise stability constant, stepwise addition of ligand take place and we get the complex. And in this complex shown on the arrow, K1, K2, K3 or Kn are the stability constant is known as stepwise stability constant of the complex. And in the second way for expression of stability constant is the overall stability constant, and the formation of complex MNN in general may also be expressed by the following steps. So in this case, what is now, this is the here metal plus ligand, this is now expressed by beta 1, EML is the complex form, beta 1 equals to product upon reactant. Now again here metal we have taken and two number of ligands, so not stepwise addition, but now ligand is added in one ligand, then two ligand, three ligand, like that, n number of ligand can be added, we get here. So this is the beta 1, beta 2, beta 3 and complex ML, ML2, MLN. So beta 1, beta 2, beta n are shown, or beta 3 also. So beta 1, beta 2 the complex is formed in this way, and this is the overall stability constant, and beta 1, beta 2, beta n are known as the overall stability constant of the complexes. And there is a relation between stepwise and overall stability constant, and this is shown here that between these two, that is stepwise means K and beta are related to one another, and there is an important equation that is shown here. K and beta are related by the equation. So beta 3 equals to ml3 upon m into l to the power 3. So this is already shown here for the beta 3. On applying both the numerator and denominator by here multiplying by the d, and here multiplying numerator and denominator by ml and ml2, and on rearranging we get. So by ml and ml2 we have to multiply to both the numerator ml and ml2. So here is here ml and ml2, numerator denominator both are through this equation we have multiplied. Then what is we get? Rearrange the term. This is not here, is it is multiplied. So ml, so first term is ml, then m and l into, this is first ml, m, and out of 3 1 l, then ml2, then another ml and another l, and third ml3 and ml here ml2, this is ml2, and another third l, and after putting this is nothing but the K1, this is nothing but K2, this is the K3. So beta 3 equal to K1 into K2 into K3. So we can write the expression in this way: beta n equals to this one term, second term up to n time. So beta n equal to k1 into k2 into k3 up to kn. Our summation of this we get this is way, or in a logarithmic way, beta n equals to k1, we can also write in a log form, log 10 beta n equals to log base 10 k1 plus log 10 k2 up to this. So this is the expression we obtain. So from this equation 1, that it is evident that the overall stability constant beta is equal to the product of successive stepwise stability constant k1 k2 up to kn minus 1. This in or other words, we can say that the value of stability constant for the given complex is actually made up of number of stepwise stability constant. Therefore we can write beta n equals to k1 into k2 equals to k3 dash kn. Or also we can write the equation log base 10 beta n equals to log k1 plus log k2 plus log k3 up to log kn. So these are the detail about this stability constant. So today we have discussed already the what is stability constant, two types of stability constant of the complex. So we have seen today the what is stability constant and thermodynamic stability or kinetic stability, what is stable unstable complexes, what is labile and inert complexes, and also we have seen the what is stability constant and instability constant, and two types of stability constant, stepwise and overall stability constant, and their relation between beta and kh, and we obtain important relation between these two. And now in the next part we are going to see what are the factors which are affecting the stability of the complexes. So today we have seen this detail about the stability constant of the complex.